So as a word of warning though, when we do switch to student presentations, we can't really record those. Okay.
No, of course not.
Awesome.
I will record mine on speech.
Okay, okay.
We'll post on YouTube so mom can see it.
Yeah, just, I don't want to violate, you know, whatever federal Canadian privacy laws exist.
So I figured out regarding Google Docs. Apparently it's cool to use Google Docs as long as you have consent from your students. So you go into lecture and, are you cool with me using Google Docs? And we go, yes, we are cool.
That's enough?
Well, that's apparently. So, but if even a single person will say, no, no, no,
Then you can't.
no way use Google Docs,
Yeah.
then, well, I won't use for you, but others you can find.
Huh. Yeah, I know that in the States in some places, even if you just say it in a group setting, someone may feel pressured to say, oh, that's okay, so that can count against you.
Peer pressure and so okay. Well,
Yeah, but if we don't have to worry about that, that's nice. What are we up to? Only one more. Okay, so we're up to 7 then. Yeah. Let's see if more people actually do show up. That'd be nice. We should be expecting more than 7. Oh. So I'll send out an email later today, but as a reminder, anybody who hasn't volunteered for a paper will want to volunteer for presenting a paper. Because it's going to happen one way or another. Okay, so I don't know if you're signed up for the course yet. Maybe?
383?
886? Okay, close enough.
Close enough?
Yeah. Yeah. Welcome, yeah. If they don't catch on and leave quickly after we start, then that's at least a sign. It wouldn't matter if you're in the other course anyway. Okay, 9, and I think not everybody's going to end up showing up today anyway, so 9 is good. Okay, so yes, I'll send out an email later today just as a reminder. If you haven't signed up for presenting a paper in the first half of the semester, do so, because your options are shrinking by the day, if not by the hour. If a whole bunch of people send in requests while I'm presenting, please don't send in a request while I'm presenting. I'll be able to see, it'll show up, right? Yes, I can inspire you to choose the paper that's Tuesday next week or Tuesday the week after by saying that next Tuesday's paper will be based on material I present today a little bit. It's related to it. And the following Tuesday's material will be related to the material that I present on Thursday. So there's at least some background. You can see there's still a lot of papers left to be taken.
Is it possible to be assigned randomly?
Anything that's not requested, I will assign.
Oh, okay, sure.
Yes.
So we don't have to worry.
Well, you might get something that you're not interested in. You know, it's okay. It's okay. But if I don't get anything by Thursday morning, then I will volunteer you for something. Okay. So have your requests in by then. But I do expect that these unselected papers probably be a little bit easier than the unselected papers further down. Probably. So some incentive. Also, since we've gotten rid of a few people with intimidation, I can now tell you that we do have a paper for Thursday. I'd like you to read it. If you looked at how long it is, it looks like it's 17 or 18 pages. I don't really care if you read section 5, which reduces it to about 10 pages. Okay? So now that we've gotten rid of people, I can reduce that pressure. But I do think it's an interesting and useful paper. Back up to 10. All right. Eventually. Yes. Okay. So, any questions about the project before we jump into material? Any questions about starting the project before we jump into the material? I recommend starting the project as soon as possible. Morning. Because if you don't, then you won't necessarily have the infrastructure working. And if you don't have the infrastructure working, you can't do the rest of the project. Okay? So it's worth starting as soon as possible so you can ask questions and make sure that things are working for you. You've seen some questions on the mailing list, but I haven't seen questions from anybody other than one person. So I'm guessing that might be a sign that not many people have started.
Is it right that you postponed the deadline till 27th?
Current deadline is the 20th?
I mean,
Or-
isn't it? It was 28th, and last time I checked, it was 27th. No? Oh, okay. Still 20th. Oh, so
Yeah.
it's 1 week from.
Yeah, so it's due in a week, which is why there's incentive. Yeah. That's part of the reason why I want you to be able to use the class mailing list as discussion about the project as well. I have no problem if you discuss the project with each other, just don't implement it for each other. So use the class mailing list. It's to your advantage. You can ask me questions, you can ask your peers questions. It's perfectly fine. Okay, so yes.
For the next paper that you are presenting, do we have to write a critic as well, or it starts with
Good
the
question.
specific?
So you do not have to write a critique for the paper on Thursday. It's just an example to show you essentially how you can present things. Starting next week, I do want you to always either write a critique or present a paper every week. Okay, so there's something due every week, but it may just be a critique, it may be a presentation. Any other questions? No, okay. So let's start off with our material then. I don't expect that we'll actually get through everything that was on the schedule today. I think we may not get to, let's go up. We may not get to testing, and that's okay. So we're gonna look at dynamic analysis. I think we'll get, we're gonna finish off static analysis, and then we're gonna look at dynamic analysis and profiling. I think we'll finish those off as well. We may not, but I think we will. And if by chance we do get to testing, I don't have any slides for it, but I'll just present it to you. There's not a whole lot I want to tell you about testing. I just want to introduce it. Okay. So let's finish off our static analysis material. So I've gone back just a little bit to where we were on last Thursday. So remember that we talked about whether or not static analyses will always terminate, and we talked about how we can guarantee termination, right, based on choosing the abstract domain and our transfer function appropriately. And for the example that we've been using, we essentially had this little guarantee where we're using a monotone framework, what we call a monotone framework. But for our purposes, you can just think that we had this as our abstract domain, right? We had -0, or we had -0 and positive, and then we had top and we had bottom, right? And the idea was that at any individual statement, the abstract state for a variable would be one of these things. And that as you perform your data flow analysis, the abstract state could only move up this lattice, right? And so since you can only move up twice, you can only visit each statement meaningfully twice, right? Okay. Yes. And this is where we left off last time, right? So we need to be able to model the program state at each statement, and that's what the abstract domain is really doing. And we have to have proper ordering, and we can use a worklist algorithm to improve our efficiency. And I asked you if anybody had seen a worklist algorithm, and everybody said no, right? So let's take a look at an example of using a worklist algorithm. So how would we actually go about doing this? This is an example of just an algorithm for performing data flow analysis. This is a worklist algorithm. How does this actually function? How can we interpret this? Well, you can see we have our same program that we had before over here, right? So we had this program, right, where we're summing the first n numbers. So we've got the control flow graph for that program over here. We've got the algorithm over here. And the way this starts out is that you create a list of work that you want to complete. So you're going to consider every basic block inside the program. Because you're going to consider all of them, they're all work to be done. right? So you add them all to your work list. And ideally, you should be adding them in the appropriate order that I mentioned last time, but we're not going to delve too deeply into that. So the first thing you're going to do is notice we start off by, for every node in our control flow graph, we add it to our work list, and we give it some initial abstract state. It starts off at the bottom, and it can only move up the lattice, right? So we're starting at the bottom. And then, while there is work in our work list, we're just going to follow a continuous process. This is the fixed point computation that I mentioned last time, where you just keep computing things until the results don't change anymore. So you'll take one unit of work, so you can see we've taken the first basic block, we take the old state, and then this is where we apply our transfer function. We look at the old state, which was the floor, and then we ask ourselves, how would we interpret the old state in the context of our new state? And remember, for the first basic block, we just set sum to 0, and we set I to 1. So sum has a 0 abstract state, and I has a positive abstract state, no matter what, because we're just defining them. Okay, so we set that into our abstract state down here, and then if old is different than new, in other words, if we've changed something, then we have to consider the things that might be affected by this change. So after that, we look at all the things that could be changed by altering 1, and what comes after 1? 2. That's the only thing. So we look at its successors, and if 2 is not already in the work list, we add it to the end of the work list. In this case, 2 is already in the work list, so we don't need to do anything. Okay? Okay, so the next time through, we'll take 2 from the front of the work list. Its old state is bottom, and its new state is sum is 0, and I is positive. And old is different than new, so well, we check and see if 3 is in the work list and add it if it's not. Okay. I'm not going through every step with this one. I'm just going over a high-level view. Does it still make sense?
No, actually, it doesn't make.
Okay.
I can't understand a thing.
Okay. So maybe I should review the example that we had first. So remember that we were computing, we were doing the data flow analysis over this particular program. We started off, sum had the abstract state 0, I had the abstract state positive because I is 1. We know it's 1 based on this statement, and sum is 0 because of this statement. Then down here, we want to find out what are the possible values of sum, what are the possible values of I, and we know that I is positive, but because of considering multiple executions, the possible values of sum at this statement were top, right? So sum could be either 0 or it could be positive. So we don't know which, so we say it's top, we don't know, right? And the same was true down at the end, because at the end of this program, sum could be either 0 or it could be positive. I is always positive. And inside the body of this loop, sum always ends up being positive and I is always positive, right? So we want to, I'm just showing you how to get these results.
And sum could be either 0 positive because of n, right?
Right, exactly. So if you jump around this loop, if you skip this loop entirely because of n, then sum could be 0.
Right.
Or even the first time through. The first time through, sum is going to be 0, no matter what, because you haven't added anything to it yet.
Okay.
But then if you ever enter the body of the loop, then you'll come back here and add something to sum.
Okay.
So the question is, how did we get these results? And the worklist algorithm is a way of computing these results, where we just keep flowing these values through the program until nothing changes anymore. Okay? Good review? Okay. So let's go back to where we were. So does that make sense then that we start off by taking 1, we figure out what the abstract state was there, and because sum is 0 and I is 1, we know this from the program. This is our abstract state. This much makes sense then.
One more question. So old is bottom. We always, at the beginning, we always put bottom for everything?
Yes. So that's why we see up here this initialization.
Okay.
In the beginning, you always start everything off saying, I don't know anything about it. And that's essentially what bottom says. You don't know anything about it. Okay. And so we update the abstract state for the first basic block. And then we look at the second basic block. It's just the next step down in the program, right? And so, well, sum is still 0 at this point. I is positive. So we end up putting that over there. In the third basic block, we've added something to sum, right? Because that's what the body of the loop does. We add to the sum. We also increase I, but we add to the sum. So both of these are positive, and we reflect that in our abstract state.
What's the second last line? Work is equal to work union?
Yes. So this is where we add things, and anything that could be affected by our change, we add to the work list, right?
Okay.
So this is particularly, so at statement 2, when we looked at statement 2 and we changed statement 2, we would look at the successors. The successors, 3 and 4, could both be affected by the change at 2, by the behavior of the program at 2. So we look at the successors, 3 and 4, and if they are not already in the work list, we add them to the end of the work list. Now they're already in the work list, so nothing changes. Okay. Yes?
I have a question. For each stage, there are 1, 2, 3, 4. They can have multiple statements, right?
Yes.
So, like, how can we say for each unit that it is for positive or negative?
So technically, you consider each instruction inside each of these units, but in this example, we're able to do this. So when you implement this in practice, you do have to consider each instruction, but it's much more efficient if you consider the instructions a basic block at a time. Because inside a basic block, you know it's always one instruction followed by another, followed by another, followed by another, right? Fair enough? Awesome. Okay, so yes, we go on to 3, and notice that this time through, we update the abstract state for 3, and we look at the successors of 3. Well, 2 is a successor of 3, right? And 2, that means 2 could be affected by the change in state at 3. But 2 was not already in our work list from last time. We'd taken it out. So we have to put it back on the end, because it could be affected. So it means we have to look at it again. It's work to be done, right? That's the underlying idea of a worklist algorithm. You figure out what needs to be done, you just add it to the end of your work list. Yes?
How do you decide the order of the blocks?
So you start off in what we call topological order, which just means that I want to visit 1 before I visit anything that could come after 1. So I want to visit 1 before I visit 2 or 4, right? Reverse post order. Once you start going through this afterward, it doesn't matter. So for this statement, once you start updating by adding new blocks in, the order doesn't matter anymore. Okay?
So it won't matter that we will visit, let's say, 4 before 3, would it? So from block number 2, we could go either 4 or 3, right?
Technically, one of them is more efficient than the other.
Yeah.
But the topological order constraints don't necessarily give you that, and most implementations in practice don't care about that, because it adds a lot more complexity to worry about that. You could worry about it, but most times you don't, because it just adds that much more complexity. Okay? So usually you just start off with topological order and you say you're done with it. Okay. Yes. So we're updating statement 3, we update the abstract state, and we have to tack 2 on back to the end because there's more work to be done. We have to revisit 2 and update its abstract state. It may be affected by the change in 3. So then we take 4 off the beginning, we set its sum to be 0, and we set I to be positive. Now this is interesting, right? Because we've already noticed that the state at 3 has sum being positive. So this kind of gets to your question, right? It might be efficient to go in another direction. We don't take that into account yet. We blissfully ignore the fact that these two things could be related because we'll figure it out later. Okay, so now we've finished everything that was originally in our work list. We've updated the abstract state for 4, and we've said that sum is either that sum is 0 and I is positive. But now we have to go back and revisit things based on what could have been affected by earlier changes. So we take 2 off the front of the work list, and because of what? We got a new sum, a new abstract state for sum. What made this happen?
3.
Well, the change at 3 did that, but because of a certain part of our abstract system, we had the meet operator, right? And the meet operator of positive and 0 is top, right? Because we had our lattice. Let me draw this out instead of flipping through the slides. Maybe that will keep it all on the board. The possible abstract states, remember, are, oh, okay, let me see if I can make that. No, that's not going to show up. There's a better one?
Well, there is black marker on this chair, right under your.
Devious. Okay. So the possible abstract states, remember, are top. That kind of shows up. Negative. Oh. Not -1, just negative. 0 or positive. And bottom. So the abstract state was 0, and we found in another iteration that the abstract state could be positive. So when we look at our successors and we take the meat of them, or our predecessors and take the meat of them, we find out the abstract state at this statement is unknown. We don't know whether it's 0 or positive. So the meet operator, in this case, takes us up our lattice. Have any of you heard of lattice theory before?
Yeah.
You have?
Chemistry.
So this probably looks a little, did you talk about meet operators? No, okay. If you had, then you'd probably be confused by this a little because usually a meet operator takes you down the lattice and a join operator takes you up the lattice. In this case, our meet operator is the join of the data flow lattice, which is completely confusing. And if you read papers on this, it's going to be a little confusing as well. So for now, just accept the fact that when I say meet operator, you go up the lattice, okay? The papers will get a little confusing about that, especially some of the older ones, but just take that for given. It's easier that way. Okay, so our meet operator is what made this happen. We're looking at the merging of possible control flow paths here from 3 and from 1 that update the state at 2, and the meet operator makes that unknown. I've beaten that dead horse. Everybody's clear on that? Okay. Finally, we take 4 again from our list, and we update its state the same way, and we get the exact same results we had before. This is exactly the abstract state that I presented to you. I've just shown you how to compute it. Okay.
Can you go back 2 steps? Yeah, so if sum has changed due to 3, you said it was 0 and 2, and in 3 it became positive. So when 2 is executed again.
Okay, so the question is, why didn't I look at 3 again?
Yeah.
Technically, I could. One of the things you can do here is kind of, depending on the order of operations, you can check whether or not the statement will be affected and then add it, or you can add the statement and then check whether or not you'll be affected. I did them one way in the algorithm and then another way when I was presenting it. So that's actually a good recognition. Based on what I've presented so far, I should have added 3 as well. You're right.
Till the time it did not change anymore.
Right, right. So what would have happened is that we would have taken 3 off, look at it, recognize that it didn't change, and just throw it away. We'd be done. Okay?
This question of this T, this up. It's the upper bound.
This?
The top level, no, the top. In the right.
Side.
Yeah, the side.
Oh.
So my question here is that if like sum, as you said, the old for 2, the sum was 0,
Mhm.
and you said something if 3 changed, which led to the sum for the 2 becoming top.
Yes.
So if sum changes anywhere, and it's different from the current state that the current instruction has,
Mhm.
and then you apply the meet operators?
Well, you don't necessarily apply the meet operator. So what happens if sum changes, then you add the successors to the work list. So you'll revisit successors.
Okay.
You add the meet operator when you have multiple predecessors whose values affect the possible states at that statement. So essentially what we're saying is, we're doing static analysis, right? So we're considering all possible paths through the program at the same time. One path may come from one direction, one path may come from another direction. In order to over-approximate and show the possible state across all paths, we apply the meet operator. Okay? So one way of viewing that is, well, one path comes from up here, another path comes from down here. And so we apply the meet operator to say, well, what could happen across all possible paths? So it's only when control flow paths merge, when they meet. Make sense? Somewhat, okay. This will be tied into your second project. But I'm hopefully not going to make that too difficult for you. It's going to be relatively simple, relatively. I think easier than your first project, I think, but we'll see. Okay, so we're done. Any questions about that then? Any more questions? Okay, so we've already seen a few static analyses. Essentially, we've seen call graphs and call graph construction. We've seen points to graphs. Points to graph construction is a static analysis. And we've seen static slicing. And we have to worry about things like may and must as well. Right? We talked about may and must issues inside points to graphs, where maybe a pointer must point to a particular address in memory. It must point to a particular variable. Or a pointer may point to a particular variable under some executions. These sorts of things affect your static analysis. May is conservatively over-approximating things, saying, okay, here's what you could point to. Must is kind of conservative in the other direction, right? You're saying, you're guaranteeing something, so it's a subset of possible. Well, that appears every time. Okay, yes. We talked about how all of these can have errors. The way in which you choose your approximations are how these have errors, right? So your abstract domain, the way you choose your abstract domain influences how you may get incorrect results. Figuring out how to cleverly define your abstract domain will determine when you get incorrect results and affect the usability of whatever you create. So we have a few different types of analyses. We've got things that are flow sensitive, where you look at essentially the possible control flow and how different paths in the control flow could affect the behavior or the abstract state. So the issue here, I guess we can say, is that modeling state at each statement is expensive. This does scale to functions and small components, but because the modeling of the abstract state at every statement in a program is expensive, it usually doesn't scale too much unless you're really careful, right? Because we had those extra annotations for every basic block or every instruction. The cost of that adds up. So you're probably not going to be able to apply this on something like the Linux kernel. unless you're really clever about it. There are some really clever static analyses that apply to things on the scale of the Linux kernel, but they do require being fairly clever about it. I
What
see a
about
question.
big data, Hadoop and stuff?
Okay, usually big data programs are simple.
Yeah, yeah. But like grab a supercomputer,
Sure.
grab Linux kernel, analyze it.
Right. So grab the Linux kernel and analyze it. You'd have to be clever about how you define it. This doesn't mean that it's impossible. It does mean you've got to be more careful. So the analysis that we saw back here, this is not a smart analysis. It more or less does what it's supposed to, but it's not very clever. If you're very clever about things, and in particular, you have to be careful about aliasing a lot. The big problem with something the scale of the Linux kernel is aliasing. If you're clever about managing that, then you can make things scalable. Okay. In contrast, we have flow insensitive analyses, which just aggregate these updates, the impact of every statement, into a global representation. Thus, they have better scalability because you just got one abstract state, a single abstract state for the whole program. And you just update that at each statement, but it's still just one abstract state. With this, you have better scalability, but because you've only got one abstract state, you have less precision. So this is the sort of thing where you might ask, does this function modify a variable? Well, maybe sometimes it does, maybe sometimes it doesn't, but you don't necessarily know whether this branch in the function could modify a variable, and this branch doesn't. You just know this function could modify a variable, right? So the flow doesn't affect your results. We also have something called context sensitivity. So the behavior of a particular program or of a particular function may be different depending on what function calls it, right? Maybe if foo calls bar, then bar behaves one way. Maybe if baz calls bar, I should come up with better names, but maybe if baz calls bar, then foo behaves a different way because of the extra variables that these calling functions change. This creates some ambiguity and imprecision in the results. And so context sensitivity allows you to recognize that the behavior of one function is different when it's called by another. So you'd be able to precisely determine how foo behaves differently depending on who calls it. That's context sensitivity. So this enables interprocedural analyses. This is what you will be doing for your second assignment. But I will have a presentation in class that shows you how to do that, okay? We will have that before you get the assignment. Don't worry about that. So can you imagine how you'd have to solve this, or what sorts of issues might arise? And what creates this imprecision from not having context sensitivity?
How is it different from the sensitive flow?
Okay, this is good question. Okay, so yes, let's get rid of someone else's lovely math. So on one hand, we have to consider control flow graphs, right? And this is where we look at the flow sensitivity. So we have a control flow graph that goes like this. And this is entry point of our function, this is the exit. A flow sensitive analysis will tell us that depending on which branch we take inside this function, the abstract state at a position inside that function may be different, right? So context sensitivity is analogous, but it's not exactly the same thing. But it's good to recognize there's a relationship between them. The idea with context sensitivity is that, again, if we have foo and, okay, I'm going to end up changing the function names that I had before, but or changing how they're related, but same function names. We can have foo, and it may call bar, right? And we could have baz, and it may also call bar. and the behavior of bar, even though it's the same code, the behavior of bar may be different depending on who calls it. Right? So in this case, it's the same code, but it might behave differently. In this case, you're just recognizing how different code could affect it. And this is based on the call graph, and this is based on the control flow graph.
Difference in behavior could be due to different, like, memory location?
Sure, potentially, absolutely. So maybe foo,
Change some memory location called bar.
yeah, or it could be even simpler. Maybe there's some global variable, and foo sets it to x equals 1, and baz sets it to x equals 0, and bar uses that global variable. It could be that simple. And the problem, well, does anybody see what the problem is? How we get ambiguity?
0 might call exception, 1 may not.
Okay, 0
No,
might
just-
cause an exception, and if you don't think about interprocedural analysis, if you don't make it precise and context sensitive, then you might say, okay, because 0 can result in an exception inside bar, bar could throw an exception, and bar could throw an exception inside foo. But you know that can never happen because x is 1. If you're context sensitive, then you'll recognize that the environment set up by foo affects the behavior and say, well, there's no exception in here. Yes?
If there are, like, conditional statements in bar, like if and else,
Mhm.
and foo executes one condition of it, and bars executes one condition of bar.
Mhm.
Could that be considered the same code behaving differently?
For our purposes with context sensitivity, yes. Because you reason about it at the function level. But yes, more or less, it's the behavior of bar is constrained differently based on the context. And there are a few ways of handling this. We'll talk about it in more detail probably next week. Okay. Yeah, we've got plenty of time. Okay, so just to recap, so if we have static analysis and we're using data flow as our static analysis tool, then we have abstract domains, which over-approximate the possible state of the program, right? So we have all these possible integers that could be stored inside some variable. We represent them by grouping things together, by saying, well, we just consider things that are negative, 0, or positive, and we throw in our top and bottom for our lattice. We then have transfer functions, which describe how each instruction or statement inside the program changes the abstract state, right? So if you add something, then, well, if you add something to 0, then it becomes positive, right? That's the resulting abstract state. And we have the bounded domain for the lattice height, which gives us termination. And we have to take care about our false positives and false negatives.
And this abstract domain can be anything, or is it fixed?
So the abstract domain will depend on your problem. In theory, it could be anything, but if you're not careful about it, you might lose some of the nice behaviors that we have. So technically, for instance, the abstract domain can still be infinite. But if it's infinite and you're not careful about how you define it, then you no longer have termination. So it's nice if you say it's finite and you can reason about its properties. And we'll look at that in a moment with an example.
Can there be other terms except the ones right now?
Oh, absolutely. So it can be domain specific. So we have negative, 0, or positive. Maybe we want to have this start out with bottom and then say, well, we have all of the integers as the next row, 1, 2, 3, 4, 5, 6, blah, 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 blah. Well, negative numbers, 0, positive numbers, but every integer separately. Then maybe at a row above that, we have all even numbers in one group and all odd numbers in another group. And then above that, we could have top, right? And so it's a different structure, but it's still showing this bounded traversal up to the top, right? Yes? Oh, okay.
And could be not numbers at all. What
It
if
could
we
be not
want
numbers at all. We'll see an example.
characters and so on?
We'll see an example in a moment.
Oh,
In a moment. And I'll even show you code for it. Okay. So we implement this using worklists, and you can speed things up by sorting the control flow graph when you're adding in the work to your work list. So let's look at an example. let's consider the goal of identifying potential misuses of files. So a file can be open or closed, right? But if you ever try to do a file operation on something that's supposed to be open and it's not, that operation will fail, right? Pretty simple. So let's try to come up with an analysis that just determines whether or not you ever use a closed file with some function call that expects it to be open. So now we see a domain where you don't really have numbers per se, but you've got these different states, right? So what should our design be? Can you think of what the abstract domain should be? Any suggestions?
Starts from close.
It starts from closed? What do you mean by starts from?
The bottom. The default value is closed. The file is always closed.
Okay, we could say that bottom is closed. So I'm just going to write up everybody's suggestions at this point. What next? Any either changes or additions?
What if file does not exist even? It's good.
Okay, so it might be the case that we don't know anything because there's nothing. Okay, that's very possible. Now I would say that if a file doesn't exist, we can say more or less closed. We can say open and not open. This is true. But I'll still agree that we might not know which of those is happening yet. It might be undefined. So I'll start with just bottom being unknown or undefined.
And we have to define operations.
Okay, we don't have to define the operations yet. The abstract domain is just defining the possible states. So based on what I've drawn here, can I have some?
Close and doesn't exist.
File
Read right.
Okay, I will simplify it and say the possible states of the file. What are the possible states of the file?
Open, not open.
Open or closed.
Right, okay. So I would say we have open over here, and then we have not open or closed. I'll say closed is good enough for me for not open. And well, we might say it varies, it's ambiguous, right? I think this is a perfectly fine lattice for it. We start off not knowing, something might be open. If it's closed along another path, then it could be open or closed, so we want the top to be, well, top, right? It varies, it's ambiguous. And if we come along two paths and they're both open, well then they'll needs to open, right? Okay, then our transfer functions, well, these should reflect the operations. The transfer functions show how the instruction affects the abstract state. So what's one way that you could affect the abstract state of a file?
Open.
Yeah, you could call fopen. You could open the file. So open will take a state that is either closed or bottom and make it open. Assuming it succeeds, but let's assume that fopen actually succeeds, because the example I'm going to show you assumes that it succeeds. Okay, what are some other transfer functions? Okay, so things like fclose will take an open and make it closed. What is fclose of closed?
Still will remain closed.
It's still going to remain closed, perhaps. You could also throw it down here to bottom,
So
because
that
you could
way-
say it's an error.
That way close should be above open, right? Because an open file is a state, it can go to closed state. So when you go up the lattice, open can change to closed.
Transfer functions don't look at the lattice structure. A transfer function says, how is this transformed by the behavior of this instruction? So the lattice shows you how multiple paths relate to each other.
But earlier we said that in a lattice you can only go up, right? So that way
yes.
you are in an open state, you can only go up, that means from open you can only
Not,
go
not,
up.
not based on transfer functions. So a transfer function can change things however it wants, right? A transfer function can take something that is open and close it. That's perfectly fine. The lattice structure shows you how to reason about the over-approximation from multiple paths in the program. But this is a very, very common difficulty that people encounter when dealing with data flow analyses. So it's good to point that out. Okay, but F open, F closed, those are the main operations that are actually going to affect the abstract state. Absolutely. One of the nice things we have here, though, is that we have subsets of some finite domain. So whenever you have this, a concrete domain, that is some finite set of states, and an abstract state that is then essentially subsets of that, you can reason about all possible subsets being the power set, right? So there are 2 to the however many elements possible subsets. Then we have this lattice defined by the structure of the subset relation. Okay? We have bottom, which is empty, where you don't know whether it's open or closed. You have the next row up, where something could be open, something could be closed, and then eventually you get up to top, where you say it's the full set of everything. And maybe if you have more than just open or closed, maybe if you've got invalid, then you'd have another row where you could say, well, I know that it's open or it's invalid. And you'd have a different row that shows those relationships too. Okay? If we have this nice finite domain, and we're looking at subset relationships, then we can use what's called a BitVector Framework. And this is a common efficient implementation mechanism for this. What would the meet operator be? Where for our purposes, we're going up the lattice. So if we have, for instance, B and C, what is the meet operator? BC. So in terms of subset relationships or set relationships, what is that?
Union.
It's the union, exactly. We're unioning things. So why is this convenient? If these are called BitVector frameworks, what might you expect?
Bitwise operations.
Exactly. You can represent the abstract state as a bit vector or an integer and just perform bitwise operations to perform all of your logic. So yes, whenever you're doing the meet, you end up performing union, and we can implement everything using bit vectors. So let's look at an example. And yeah, this is nice. Okay. We have, oh, that is not.
You need to change background on white.
Yeah.
There, color scheme, and that's it, I guess. So color scheme,
Ah, there we go. Yeah.
and then let's check something.
Something.
Mac
other than
basic.
that. Yeah. Let's. Done. Is this legible?
That's better.
Better, but maybe not legible.
No, it's
Good.
You can see.
Okay. So let's look at one implementation of this. And the code isn't exactly clean necessarily, but it's clean-ish. Okay, so we can see here I've got something called a file policy pass, which implements a pass inside LLVM that does exactly what I just said. Does exactly what we just came up with. And you can see that this part is printing the results, and all it does is look through all of these errors that are reported and prints out a line number, something that you're going to be doing in your project, right?
Oh.
Suddenly we're interested. And then prints out the actual error that occurred. Okay, so if we go up, well, here you can see code for printing out the line number. Interesting. That might.
It's recorded, so it's going to be on YouTube. Yes.
Okay, and we can see here some code that does the run on function. This is the main code for the pass, right? This line up here computes the data flow analysis. This does the entire data flow analysis, and this interprets the data flow analysis and finds the actual bugs. So given the data flow analysis results, in particular, we have this part which finds the errors. Once we have the results, we go through and find every call, and we look at the function that was called. And if it was an fread or an fwrite, and the third argument could be closed, then we record an error and say, oh, the third argument could be closed and it's not supposed to be. If we have something like fprintf, fflush, or fclose, and the first argument might be closed, then we add an error for the first argument. Okay? So this is the presentational stuff, how you actually find the bugs once you've computed the data flow analysis. Where's the data flow analysis portion? It is right here. But first, I'm going to show you a worklist class. Very simple. We have a list, and we've got a set. So what we can do is add things to the worklist, and all this does is say, well, if something isn't already in the worklist, push it on the back. And I can take things from the worklist, and I just pop something off the front and takes it from the set as well. Removes it from the set of things in the worklist, right? Very simple stuff. But we can compose them nicely. So what does our data flow analysis do? Well, it computes these abstract states for the files. We start off by initializing the abstract state for everything to bottom, the default constructor for state map. And then we add everything to our work list in reverse post order. Conveniently, there's something inside LLVM that creates a reverse post order for you. And then we have our fixed point computation, where we take something from the work list, we compute the meet, we apply the transfer function to get the new abstract state, and then if things changed, we add the things that could have changed to the work list. And that's it, right? It's exactly what I told you, just implemented as I told you. Question? Okay. There was a sigh. Okay. And then up here, you can see the transfer function as well. Now, the transfer function is a little bit unexpected in some ways. We start off by saying, well, we don't handle anything that's loaded from memory. So this is a pretty naive analysis. It only considers things that are passed into functions or things that are created right in a function, nothing that's stored to memory, right? And we also have to perform another meet here, which we didn't talk about before. A phi node, in practice, represents a meet among possible paths, right? So the transfer function for a phi node is itself a meet operation. Okay? I see confusion. Someone wants to express the confusion?
So how are we using this phi?
Okay, does everybody remember what a phi node is? I should put it that way first.
So as you said, like the different ways of initializing the variable, we put it all in one statement and then
Right. So because we have SSA form, a phi node says, well, if there's only one definition for every variable, then for things that might have multiple definitions, depending on which path you take, we need a special instruction that creates that definition, depending on the path. So, maybe along path 1, you have one value, and maybe along path 2, you have a different value. And this just selects which value you get based on your path, right? So because we're looking at possible values from different paths, we have to take the meat of them. That's it. Make sense? Much clearer? Okay. But because we have SSA form, we have this extra grittiness where the actual transfer function for the phi is a meet in and of itself. We've got meets in multiple places. So then after that, we look at the instruction. Well, we see if it's a call site, right? And if it's a call to a direct function, or it's a direct call to a function, then we just see if it's an fopen or fclosed. If it's fopen, we change the state to open. If it's fclosed, we change the state to closed. And that's it. That's the whole thing. That's all it does. And in terms of the implementation of the abstract state, you can see I've got file state unknown, file state open, file state closed. How do those work? Well, file state is just an enum. And we have 0 for undefined. We've got open is 1, closed is 2, and unknown is open or closed 3. Right? So it's just a bit vector. It's just a bit vector. And as a result, if I want to take the meat of two different file states, it's just the OR. It's just bitwise OR, right? So let's see if this works. Okay, so I have some examples here. We can this also doesn't show up too well. I can at least make it bigger. That much is easy. Let's make this.
Yeah, black and white, just
Oh,
color.
yeah, there we go. Oh, did it? Okay, I guess I have to move the cursor around all of the other options to make it stick. Okay. Legible, well, the green is not so legible. Everything else is legible. So we have a simple function, right? F open, printf, F close. Should there be a bug? Should we find any bug?
No.
No, right? Because we open, we use it, and then we close it. So let's see if we find a bug. I've got a little script here that runs the program. No errors detected. Good, right? So, this one, we have F open, F close, printf. Should we find a bug?
Yes.
Yeah, especially since the name of the file is linear buggy. You should expect to find a bug, right? So, yes, we should find a bug. And we do. At line 7, and call the fwrite argument 3 may not be an open file. Right? Nice. Okay. Yeah,
Magic.
Okay. That's the response I like to hear. Yeah, and this remember I said was something simple, something naive, and yet it's magic, right? That's pretty nice. So we can look at something even a little more complicated. Let's just go right to the end, and then maybe take a break for 5 minutes, and then come back for the other material. So here's a loop. Well, okay, inside this loop, we can iterate 10 times. We fprintf, we fclose inside the loop, then we fopen again, and then depending on the possible condition here, we may or may not close. So this is more complex, right? One, we've got loops. That makes things messy. And this may or may not close things. What happens if this doesn't close something? Well, then we can print stuff out here, we can close it. We can print stuff out here, we can close it. If this does close things, then, yeah, these would be buggy, and these would be buggy. So let's see what happens. Okay, 4 bugs. Nice. It tells us exactly which functions were called, exactly which arguments were invalid. Okay. Is it still magic? Is it comprehensible magic?
But okay, so it's showing 4 potential errors.
Yes.
But it doesn't tells you the root cause of the error, right?
Aha. This is a good question. The definition of root cause is very subtle.
Right.
So if we look at our program, now I should say there are static analyses, more clever static analyses can be more insightful about that. And in fact, there is a tool called Playing Static Analyzer which tries to be more insightful, but as static analyses try to be more insightful, at this stage, they're still somewhat burdensome. If we look at the code, though, maybe this is correct. Maybe there's supposed to be something else afterward. So what is the root cause? It's ambiguous. You can't necessarily tell what the cause is based on the code. Now what we could have done, but I didn't do, is say that it was closed at this line. That the file wasn't open because it was closed at this line. That's the kind of thing that does exist inside static analyses now. It's a little bit more informative that way, right? That would probably have been helpful, but it still doesn't necessarily mean this is the root cause. Is that okay? That's clear. Okay, so let's quickly finish up this static analysis business because we just have a few more slides left. Okay, so wrapping this up, we can have forward or backward analyses, right? Sometimes you want to look forward and see what happens as a result of something, and just like with slicing, sometimes you want to look backward and see what may have caused something that you observed. And you also have things like may or must, where depending on whether you want to determine if something may be true or if it must be true, you might use either union or intersection as your meet operator. And we also have to worry about these sensitivity issues. Path sensitivity, flow sensitivity, and context sensitivity. We didn't talk much about path sensitivity. Okay, yeah, let's do that very briefly. Can someone come up with a scenario where the analysis that I gave you, or that we just looked at for files, would lie? Where it would tell you that something was a bug when it was not? Where it would tell you that a file could be closed when it was actually guaranteed to be opened?
In the first case?
In the first case, it was correct though, right? In the first case, it told us there was no bug.
No, in the there was, can you go back to the, so it said that when the loop started, it wrote something in the file, and at that time the file was open.
So you mean in the loop results, where it tells us that the file operations at the top of the loop
Yeah.
are buggy? Well, the issue there is that those are buggy if you close it and then go back around. So that's actually a legitimate bug. But there are cases where you can get a provably incorrect bug that is reported because it's a static analysis, right? Because it's not infinitely smart.
So basically that path will never be executed.
Aha, a
But
path
when you
that's
take
not
a
executed.
static analysis, you consider it.
Right, right. That's exactly the issue. There's a path that cannot actually execute. So
I thought maybe conditional, like branches.
right. This is absolutely on the right track. Can we be more descriptive? Let's say I've got if C and then
Open some file.
Open some file.
okay, F open, blah blah blah, and I say F equals this. Then what else?
At the end, close the file.
Okay, at the end, close the file.
So it means like that the programmer may be sure that the if condition executes, but so the file is open and then closed.
Okay, I think we can make it more self-contained. We can show why the programmer is certain that this executes.
Okay, just maybe if C and else, two statements are there, and if C is say an unsigned integer, then it will never be negative. And suppose we have some condition, if some programmer wrote an else condition for
This
a
is still
negative
awfully
case,
complex. I think we can simplify it even further.
If f not equals null, could it be?
We can even just say if C.
Again?
Yeah, this is a pattern that occurs a lot in real code.
Okay.
It's depressing that it occurs a lot in real code, but it does. So you could have if C, F equals F open, and if C,
F equals
F close, F. Well, we know that because C is the condition in both cases, that F is open here, because we opened it right here. But conservatively, well, along the else path here, we don't know that F is open. So when we merge the state at the bottom, the meat tells us the state is unknown, it's top, right? So if we close it, we get an error, even though we know that it can't. This is an issue of path sensitivity. Now, there are ways to make path sensitivity a little bit feasible to a limited degree. The question is where you draw these boundaries, how you make your abstract states, how you make the analysis work in a clever fashion in order to have a degree of path sensitivity. One of our papers later on talks about that and using it for proving that a program is correct, which is kind of interesting.
So can we just merge the two blocks? Say if we know that this condition will occur only if the first condition occurs.
If they occur, if they're lexically close, if they're in the same function, that's easy. If they're separated far apart, if C happens to be something that's done through a pointer, and this happens to be the case that it's guaranteed to point to the same thing, but your pointer analysis isn't precise enough, it's tough to tell. It's tough to tell in practice. That's the issue. It's very simplified. Even this actually does happen. Even this stupidly simple example does happen.
So in this case, you're saying that the C condition doesn't change, like when going.
Yeah, same condition, the exact same condition. That actually does happen, right? So we open it up here, we close it down here. The condition's got to be true in both cases, so we always know that the open is tied to the close. But the program is structured to make that difficult to interpret. That's path sensitivity. Okay. And in practice, this is really, really difficult because the more if statements you have leads to a combinatorial explosion of the number of possible paths, right? Here's 2 choices, here's another 2 choices, so that's 4 choices. Another 2 choices means 8 paths. Another 2 choices, 16 paths. And so we've got a problem, right? Okay, so let's move on from that. Other traditionally static, we looked at data flow analysis. Other traditionally static systems are type-based analyses, bounded state exploration, symbolic execution, and model checking. We will see several of these, not all of them. We'll see several of them in the papers we look at. And I might talk about them a little bit before we start to introduce a new concept. Just a little bit to introduce enough. Okay. It also turns out that increasingly we incorporate these into dynamic analyses. So yes, summarizing things, you're considering all the possible behaviors across all executions, and you have to approximate things to fight this undecidability, to fight the fact that technically we can prove that most of what we're doing is impossible if we want to answer it precisely. Okay, so that's the end of static analysis. Let's take a 3-minute breather or what have you, I don't know, loosen up and get prepared for dynamic analysis.